See my screen in the full screen mode. So let us start our Kharkiv quantum seminar, and I will say a few introductory words in relation to this first seminar this academic year. The seminar is organized in Kharkiv. I'm broadcasting it from ILTPE, probably next door to where Yuri Semyonovich you were residing, from the room 405 in theoretical building. The organizers were me, Sergei Shevchenko, and Andrei Sotnikov. By organizing this seminar, we aim several targets. Firstly, to bring together Ukrainian and foreign scientists to sustain motivation and enthusiasm of Ukrainian physicists, and to motivate and educate young researchers. Usually, the seminars are scheduled 2 times a month on Tuesdays, and the time is different. Today, our guest is from Australia, where they have now several minutes past 6. Usually, we ask speakers to have the talk of about 1 hour, and then some 40 minutes, depending on the tiredness of the speaker and on the enthusiasm of listeners. One slide about our experience with these seminars. Last year, we had 9 months of seminar, and interestingly, from Kharkiv, we delivered, we broadcasted 18 lectures in these 9 months. And we hope we'll be able to continue this year similarly. If you are interested, the presentations and videos are available online on the seminars webpage. We have several seminars scheduled for this year, which you can see, and you can also find this information on our conference site. And with this, I would like to introduce our today's speaker, Professor Kivshar from Australian National University, M in the 3rd degree, Metamaterials, Metaphotonics, Metasurfaces. And one slide about our today's speaker, briefly. Yuri Semyonovich received his PhD degree almost exactly 40 years here in Kharkiv. Then he left the Soviet Union, and after several visiting positions in Europe, he settled in Australia in 1993. He is a fellow of the Australian Academy of Sciences and also a fellow of several famous societies. He received many awards, and recently a very famous Max Born Award of the Society Optica, formerly known as Optical Society of America, for outstanding contributions to physical optics. This award is given one per year. His research interests include nonlinear physics, metamaterials, and nanophotonics. And hopefully, we'll enjoy the next hour listening to Professor Kivshar. Please, Yuri.
Thank you, Sergey, for introduction. I was very much surprised to see that seminar and watch some of these presentations. Was very, very unexpected. Anyway, today try to put some very basic knowledge of what we are doing, because I'm not very much familiar with audience, and will be many very simple things. But unfortunately, yesterday was 1 year since we lost our friend and colleague, Sergei Gridescu, who was a frequent visitor in Australia because his sister moved to Australia, immigrated to Australia, also brought his parents, who passed away here in Melbourne. And Sergei was visiting Australia very often, and we collaborated with him. And low temperature physics will have a volume 12 devoted to some research papers in memory of him, and also some comments about his science and life. That's absolutely unexpected, and reasons for that, and terrible. It's very difficult period now everywhere, and I'm really sorry about your situation. What I wanted to present today and talk about metamaterials, how this appeared and why it's exciting, and then move to meta optics, metaphotonics. Of course, meta became very popular these days because of meta media type of sites, and meta means beyond in Greek. So this initially was suggested to describe materials which are artificially made with properties which do not exist in nature. I will talk about recent advantages of metaphotonics, bound state in a continuum, resonances. We'll talk about metasurfaces. Of course, for people not working with light, I just want to show this very impressive photo, how you can see light. Light appears to be generated from sun and from incandescent light bulbs, and of course light is everywhere, and even here we have a lot of lights who allows us to see many objects. But in physical application, we talk about light like special part of the electromagnetic spectrum, but it's a special fraction of electromagnetic waves, which range from radio waves to gamma rays, and the visible light actually take only fraction of that. So generally, we talk about electromagnetic waves in general, assuming that light is just part of realization for particular purposes. If you go to see how light interacts with objects, basically what we see major scenarios when the light just absorbs, and this disappears, no reflection, we basically don't see anything, and no transmission. Of course, reflected light allows you to see objects in different colors depending on type of reflection. And of course, there is intermediate case when light transmit, partly absorb, and that's usually how we present light interaction with objects. If you study scattering of light, usually what in the ray optics, what we see is that light is scattered backward and sideways, and object create some shadow. But if you want to actually control light, like we want to basically make light transmitted through the object, and in particular creating what we call invisibility clocking. So region which covered here will be not seen because light will look like transmitting through without reflection. We need to put kind of cover of that region and try to bend light. So bending light is actually condition to create this type of invisibility clock, and it's not very trivial how to bend light, because usually light is reflected and transmitted and absorbed according to very simple rules, very often discussed in the textbook. At some stage, people wanted to create so-called invisibility cloaking through this creating of the shell, which would allow you to hide object inside. And these objects actually can be placed inside of that cavity. And if we manage to bend light, you basically will not see reflection on transmission. And actually, we can hide anything in so-called invisibility zone. And this basically concept of this invisibility cloaking or device which will bend light. Question is how to manage bending this light to avoid reflection. This bending can't be done by usual way because we need to actually change our principle of reflection. Usual reflection occurs when we have interface between dissimilar materials like air and glass, and this law of refraction, changing of trajectory of light when we cross the boundary, is defiance of so-called Snell's law, which is well known in the textbook. It depends on density of material, so slower or faster, and this reflection actually manifested like a change of trajectory. In order to see refraction, you can do it at home with a very nice experiment. There are some very simple physics experiments, I think presented in the book of Perelman, when you have a coin hidden in a glass in some bowl, but that can be seen when you put a pencil in water. You see that this laws of refraction, which allows you to see the part of the of your pencil like bended. So that's produced by usually laws of refraction. But if you want to, it should be working, no? Okay, sorry. Let me do it. I lost the movie. No. Anyway, that's not. Anyway, this was the idea to show negative refraction. So light propagating in the opposite direction when we are talking about special type of media. And the special type of media is called left-handed media, and it's artificially created like a type of metamaterial. Unfortunately, my movie not working. I forgot to check it. This type of clocking fabricated for microwave. People studied that, and basically, I don't know why it's not working. Yeah, you see that the shell, which allows you to bend light in the opposite direction through negative refraction, and the light plane wave propagate, and this hidden region can be used to actually hide light. This clocking is possible only, we were involved in that type of study some years ago, creating these funny devices to hide objects in microwave. This clocking is possible, and wrong bending of light is possible due to concept of metamaterials. Metamaterials appeared, actually the main concept appeared long time ago, but it was much later realized in experiment. An idea very simple, like nature create all substances through arrangement of atoms and molecules. We can do it with artificial structures, which are different shapes, two-dimensional and three-dimensional, arranging subwavelength elements. These subwavelength elements, which are called meta-atoms, and were designed to support different type of resonances, which will change macroscopic response of material. So wavelength of light is much larger than these elements here. This produce properties, macroscopic properties of materials, which can be engineered at will, being different from what nature can offer you with usual materials. What is the original concept? The original concept for metamaterials made for electromagnetic waves or for light was to use two types of resonances. One resonance is so-called electric dipole resonances, which are supported by metallic object due to excitation of surface plasmons. This can be achieved with metallic elements. Other type of materials which can actually allow you to engineer magnetic response is the first example was a so-called split ring resonator. When you applied fields, you create oscillating electrons, and it creates a effective magnetic moment, which can be combined with electric moment with a structure which can actually vary properties of materials. One of the properties was so-called refractive index, which is product by epsilon and mu, electric and magnetic response material parameters. And the people had the fun to actually engineer values of refractive index. So refractive index of common materials is a product of mu and epsilon, positive. And that's if you take square root from positive, refractive index positive, and what exactly enters Maxwell equation correspond to what we see in real life with water, with any materials. But if you're able to engineer response, you can change sign of epsilon or sign of mu. And the most interesting opportunity, actually first speculated by Victor Vesilago in 1968, was to take the case when both epsilon and mu negative. If we are both negative, product positive. And in Maxwell equation, what is enters Maxwell equation actually n squared. So n can have both first negative and positive sign, and if you have negative, refractive index becomes negative, and this means that we can still have propagating waves, because propagating waves defined by a sign of n squared, but in reality, refractive index will be negative. That was speculated by Victor Vesilago and then John Pendry in 2000. And initially, it was just came like a simple concept. And the important component, of course, to have a magnetic resonators. The paper was published in 1968, and as you understand, is not very scientific journal. Because normal journal did not accept that paper, that was a kind of speculation what will happen if we have materials with simultaneously change values of epsilon and mu with simultaneously negative epsilon mu. In 2000, it was a paper published in PRL when people actually realized this type of metamaterial response by engineering resonances of two different elements, of electric rods, which supported electric dipole resonances, and magnetic splitting resonators, which supported magnetic modes. So combining magnetic and electric responses, we can create a composite medium, and which had a simultaneously negative permeability and permittivity. And so basically both negative epsilon and mu. That was a lot of fun, and was in Optics Photonics News as a flagship journal of Optical Society of America. It was a special feature issue, which feature article which describe milestones of this field, from the first structures from first structures created in the microwaves, and then the fabrication of different type of devices, including the visibility clock, as I mentioned, and engineering basically epsilon and mu responses. That was a lot of fun, a lot of hypes, and we still expect the opportunity to get for these guys to get Nobel Prize. Actually, it should be announced later today, but I don't know. It's very difficult in very sharp competition of different achievements. What is interesting that for a long time it was perception that if you take, for example, metal dielectric metal type of structures and look at the average parameters, they basically may achieve conditions when parameters become negative, but in reality there are a lot of effects which are driven not by average parameters, by resonances. Before going to that, I will show you several examples. One example in modification of MRI with using of metamaterial structures. It's based on the fact that you can enhance magnetic resonance and reduce time which patients spend in the MRI camera. And that was original paper published in collaboration with ITMO University, and 2 images of fish which show you images of fish without metamaterial, in metamaterial, in professional MRI camera. The second example is probably not as critical now after COVID, was developed several companies. It's advanced security control. We create a type of this metamaterial antenna arrays, which allows you to trace, like you usually trace in airport when you pass this security gates. And this just, you don't have that bottleneck. You just walk and the antenna detects some suspect who will be further checked, and this will may reduce substantially the time people spend in security. It was a prototype fabricated because my student was involved in that in America, and that's why I know details. So, but I'm not sure now after COVID that this became critical, and if we produce some real installation in airports. And some years ago, I traced applications of metamaterials, and you see that then there was a growing business, and basically the business involved industrial application, but mainly microwave and terahertz structures, which has this both electric and magnetic response control. And these are some attractive opportunities in the metamaterial market in 2002. I didn't trace it more recently, but that was a kind of very interesting application of this field to different type of antenna control. Of course, this all stealth technology, which makes some military object invisible, were all based on the concept of advanced antennas and metamaterials. Even people originally did not call them metamaterials, but now we understand that this origin of all these types of effects of invisibility are very, very related very much to this metamaterial trico concept. For some stage, it was a development of different type of structures. All the structures based on metallic elements. So these are all metals. This is what we call nanoburger metal, dielectric metal type of structure. We're all based on the fact that we can excite so-called magnetic modes. The magnetic, even here, very complicated structures, metal, dielectric metal. So we support magnetic dipole resonances, which allows you to create effective magnetic moment after elimination of electromagnetic field in non-magnetic materials and control magnetic component of electromagnetic field. So if you're able to control both electric and magnetic component, you're basically dealing with metamaterials, and you basically have a possibility to control fields similar to what usually people do with radio waves. An idea was to actually go to optics, And for that, of course, we need to revise completely the philosophy of metamaterials. And that philosophy was originally based on averaging, but we need something else. At some stage, term meta-optics appeared, and you may trace this word, and many famous people use this title for different application, even for metawaves. But first time I came across this term was in 2011, when my colleague, now Professor Emeritus of Sydney University, Ross McFadden, who is known for his theoretical studies of electromagnetic theory, suggested to use title Meta-Optics in our review paper, which were written some years ago, invited review paper for NPG Asia Materials. He insisted to use that word, and somehow I did not pay much attention. I'm quite flexible guy. I did not reject it. And after some time, when this word became popular, I asked him, Ross, can you basically remember what you suggested? And this is his explanation. He basically tried to bring ideas from metamaterials, possibility of controlling electric and magnetic responses, and bring them to traditional optics, which that time in 2011 did not exist whatsoever. I mean, it's actually did not exist because majority of concepts were verified for microwaves. What we need basically something different, and the something different came with the Me theory. Gustav Me is famous for a very simple fact. He was theoretician, and he solved Maxwell equation exactly for plane waves, which you see that his crocodiles, he did not have Mathematica, and he solved Maxwell equation exactly through this analytical expression for special function. Now we basically may physically classify the solution, introducing dimensionless parameter, and this dimensionless parameter is radius of the sphere, wavelength of light, and of course many phenomena I should describe as his formula. That's why Me theory is very well known, and basically his formula also match with geometric optics solutions. But we are interested in so-called Me resonances. What is Me resonance? This is if a plane wave comes to interact with sphere, it penetrates inside of the sphere, and the wavelength of light inside of sphere becomes lambda divided by n, where n is refractive index, and lambda divided of n becomes comparable with geometric size of the sphere, and that's how resonance appears. This, believe or not, these pictures is from his 1908, so many things are known for a long time, but we're just waiting for their application. And if just you want to understand what kind of Me resonances, oh, it's working, wow. This is a simple experiment. You can do it home, but don't do it. So basically, if you put two grapes in microwave in a grape becomes comparable with the size of the grape, excite Me resonance, and this is type of plasma appears due to excitation of the strong resonances in grapes. So this is a manifestation of Me resonances. Actually, it's appears in the original paper. Some guys, my friends, measured Me resonances of Apuncia leaves. So basically, any type of dielectric supports these resonances. Now, if I look at the sphere made of silicon and look at scattering cross sections using Me theory or direct numerical simulation, here it's Me theory because it's circular, allows exact solution. You see there are two peaks. One peak is magnetic dipole resonance, shown here. Second peak is electric dipole resonance. So basically, sphere made of silicon support resonances in a visible wavelength. You see that's a visible spectrum. So it can be seen in a normal microscope if you support this resonances. And that was known, as I mentioned in the paper, but was not realized for a long time that it can be useful in metamaterial. But if you remember, I mentioned about magnetic and electric response, and you see the single sphere may allow you to create both type of resonances, electric and magnetic. It's maybe created as an element of metamaterials. But what else we have here? Because spheres usually very large, relatively large, it's several hundred nanometers made of silicon, they support also multipoles. So electric dipoles, magnetic dipoles, electric quadrupoles, magnetic quadrupoles, all these multipoles are excited from single source, they're coherent, and they can overlap. This overlapping or interference is very interesting effect. Of course, everybody knows about interference. So interference can be observed when you have two sources which emit radiation, what any type of waves, and then wave propagating away from sources will create a maxima and minima, destructive and constructive interference. But here we can have a radiation created by different types of multipoles, electric dipoles and magnetic dipoles. These multipoles may interfere being created by a single source. So this is a kind of non-trivial generalization of interference concept, and that may lead to actually suppression of radiation in one direction. This is basically shown here. It's also created originally from purely theoretical work of Milton Kerker, who also studied some new materials which did not exist in nature, where epsilon and mu coincide, and he predicted this interesting Kerker effect. When you have radiation created by electric dipole, radiation created by magnetic dipole, maybe overlap, and actually you can create unidirectional scattering. So interference will lead you to unidirectional scattering. One dipole, another dipole, basically they overlapping in one single source, and they create this interesting pattern. This is the illustration. We have an array of dipoles here. We emit to both sides. It's a typical dipole radiation. Magnetic dipoles radiate similarly, but we have a bit different field structure. But now, if I will place together, it's actually exactly solvable problem. If I place them in one array, both electric and magnetic dipoles, we will actually produce this interesting interference effect and cancel all radiation to one side if amplitudes of the sources will coincide. So this is a Kerker effect, which interestingly can be used for many applications, including very special type of metasurfaces. Another things which appeared here, which was discovered also accidentally, was possibility to excite high Q resonances in these structures. So what is the physics of that? The physics of that associated with so-called bound states in the continuum. For bound state in the continuum, we need to go to quantum. This is a quantum slide for quantum seminar. So they originate from very short and unknown paper of von Neumann and Eugene Wigner, founders of quantum mechanics, or some of founders of quantum mechanics. This paper is very short, and that basically presents exact solution of Schrödinger equation with very strange potential, three-dimensional. And this exact solution fully localized. But to explain possibility of the solution, I use a sketch. So this is a typical textbook quantum problem. Quantum problem which describes behavior of quantum particles in a potential well. And of course, everybody knows that we can have propagating states which usually occupied energy zero above, positive energy, continuum spectrum, and discrete states which correspond to localized or discrete values of energy. This is very well known. Solution which was found by von Neumann and Eugene Wigner correspond to a bit different potential. And again, remember, it's three-dimensional, so I don't show the solution itself. It corresponds to this sketch. So imagine that we have a potential with varying varying ages. So we also use sinusoidal divided by radius, so decay in sinusoidal potential. Now all energy spectrum is divided not in two, but in three domains. And here we have a tunneling through this maxima. So we have way which tunnels get reflected, tunnels reflected, and you can find conditions, not always, but for some specific cases, we can high condition, but these reflections and transmission can cancel each other. You can create a fully localized solution which exists above energy zero, so sitting in the continuum spectrum. And this is what we now call bound states in the continuum. So these bound states in the continuum, they just exist like a curiosity, like special conditions which support these localized states, which very hard to realize in practice. But importantly, in physics, if you approach these conditions of suppression of radiation, we can actually try to achieve highly localized states inside by tailoring the radiative part of this mode. So that's why we call them quasi-bound state in the continuum in different applications. There's a lot of efforts to study origin of these states. I just few papers I show after that, but it was absolutely no physical interest. These are mathematical papers and basically published in like a journal of physics or PhysRev A. But it was a first paper from optics, also theory paper came in 2008 for very realistic conditions. And then it was several efforts to get these states in a discrete array of resonators. This is one example. So array support propagating modes. So array of waveguides and two defects support localized modes. If you tailor these modes in that way that we cancel leakage along the waveguide, you can get the fully localized states which can be observed in experiment. This can be done in the age. So I was somehow involved in that fun, but that was also experiments, by the way, in the waveguide arrays. And the Moti Segev group also produced experiment, but it was kind of fun. But then a very big boost for bound state in the continuum appeared in connection with the studies of photonic crystals. Photonic crystals are slab of dielectrics with a structured, usually periodic arrays of holes or resonators. So we now, these days, we call them metasurfaces. And in such structures, we observe a type of standing waves which do not emit radiation above and below. This is a type of waves which are fully classified like bound state in the continuum. What is the idea of that? If you have a slab generate propagating waves, forward and backward propagated waves. If you modulate this slab, we create flock states and we try to interfere. And with this interference, we have destructive and constructive interference. And we can, when we have a destructive interference, radiation outside is suppressed. If you look at the cross section, this is very similar to this quantum potential with periodically decaying tails, which I discussed previously. And this mechanism allows you to suppress radiation outside. And this basically creates standing waves, which will be decoupled from radiative, from continuum spectrum. So that's how this bound state in the continuum appears. Complete destructive interference. Somehow people who study solitons may remember some efforts to describe coupled states of solitons. This coupled stage which appears in the presence of higher order dispersion, which produce radiative tails of solitons, and then when combined to solitons, we suppress radiation from outside and get fully localized two soliton states, which still exist in continuum spectrum because it's radiative solitons, but can be classified like a discrete set of the solutions which fully decay in tails. Anyway, this is a type of solution which we have in the slab. So it's standing mode, which exist in the continuum spectrum, so it's supposed to leak, but it does not leak because of symmetry and cancellation of radiation. But there are at least 4 major mechanisms of creating of such states. One of them is very well known mechanism which associated with so-called Dux mode. Dux mode discussed in many applications in plasma, where appears through mechanism of strong coupling, so repulsive interaction of 2 different types of dispersions coming from 2 different types of modes. And when you see this strong couple mode diagram, usually it's associated with the states which people call Dux states. And Dux states means that modes which exist here, it decouples from continuum spectrum. So this is so-called mechanism which associated with interferon resonances and appearance of bound state for interferon resonances. This is another mechanism to have localized states. Some years ago, we discovered that very simple open resonators made of high index dielectric can support this strong coupling mechanism and this quasi-bound state in the continuum. Why it's quasi? Because epsilon is still finite, so it will be fully bound state in the continuum if we take larger and larger values of epsilon. But if you don't have if you have intermediate values of epsilon, these are highly localized, but not exactly localized solutions. Here, mechanism is mechanism which associated with 2 types of mode, me resonances in that plane and Fabry-Perot resonances when we vary height of these resonators. I just remind you that this is open resonators. There are no mirrors, usually lasing from cavities organized by placing 2 mirrors and modes which trap between mirrors. These are completely open resonators. And modes are trapped through the mechanism which was known since von Neumann and Wigner, suppression of leakage mode, which is going outside of these resonators through the possibility to excite 2 modes which will overlap. This overlapping is observed here, like interferon resonances, 2 types of modes, me-like and Fabry-Perot-like, will produce these Dux states and allow you to localize dramatic localization of energy in open resonators. Of course, it was a series of experiments. Microwaves much easier because we can use ceramics with very large values of epsilon. And with optics near infrared, we can use aluminum gallium arsenide structures, which also support relatively high values of quality factor. So it's very narrow peaks here. Usually for subwavelength optics, values of Q factor of a few hundred is enormous. It's an enormous number, which allows you to observe many interesting effects, including very strong nonlinear effects. A very recent direction came from completely unexpected perspective. If you look at the me solutions, it's an exact analytical solution, and everybody assume, talking about me solution, that we are talking about sphere made of solid material and wave coming from like vacuum and scattering by the sphere. But it's a theoretical solution. It actually assumes different values of parameters. And in fact, the solution also describes a case when sphere is made of air and surrounded by denser material. Also, you can apply the me solution to this case. In this case, you also have modes. These modes, waves localize in empty cavities, so light trapped in cavities. Very similar mode. This is their dispersion. Also electric dipole, magnetic dipole, quadrupole modes. And of course, if you go to real materials like silicon, of course, behavior and features are defined by real values of refractive index and losses. If we take a normal spheres, as the region where losses are strong, this K or kappa loss is strong, so there are not much seen in quality factor. They don't allow modes to localize. and localization happens only when losses becomes very small. This is a real case. But for inverted case, it's just opposite. Losses help to trap light inside, so not only large values of refractive index, but also losses. So you have a walls which are very tall walls, but also lossy. So light get very nicely trapped inside. So this is actually a consequence of missolution from 1908, which was understood only recently for this inverted case. So we call them Mi voids. And these Mi voids can be realized in much simpler geometry. Of course, you can't do entirely three-dimensional voids, but we can drill some cavities in a solid materials like silicon. This is not metallic membranes because we're not open holes, but we're just finite depth holes, but we still can support very nicely very nice modes. Modes are characterized by different colors because we have different frequencies associated with different colors of visible spectrum. And then we can study them in details, and these modes can be used to actually achieve so-called structured colors. So group which we collaborated, actually the modes were discovered accidentally by Mario Henschel, who is a fabricator in the Stuttgart group. And then he decided to reproduce Kandinsky painting, which is the only Kandinsky painting in the Stuttgart gallery. So basically, he created structure by drilling holes of different depths and radius. These are elements of that, which reproduces only a piece of that, but he did it larger. And then you can see that you can reproduce colors by with these voids. In fact, there is Optics Photonics news last April, which discussed different ideas for structural coloring and in particular voids. And we present the story that the Stuttgart Gallery installed microscope to see next to the picture, which you see Nano Kandinsky painting, which is based on all these ideas of different colors supported by these semi-void resonances. Anyway, these developments of SMI resonances application, high Q values, created field which is these days have a name of Metronics. The name appeared after we were interviewed in the conference in Singapore by editor of Nature Photonics, Rachel Vaughan, and my colleague from Stanford, Mark Brongesma. He basically said, oh, it's probably kind of Metronics, which we may call in honor of Gustav Mie, who created this exact solution. So now this Metronics, based on resonances, and we may discuss different type of application, and different type of application also involve topological structures, which play with different type of resonances, of course, nonlinear optics and nanolasers, generated light from specific modes supported by Mie resonances, structural coloring I already mentioned. But very active field now is the so-called metasurfaces. These are front cover of issue of Advanced Materials with our structures. It's actually structures fabricated from different type of metasurfaces. So metasurfaces are planar array of resonators which support either local or extended modes and allows you to produce different type of functionalities. So very primitive idea of metasurfaces in this very old slide of my friend from Harvard, Federico Capasso. Basically, if you have surface, you use a Huygens principle. Huygens principle tells you that if you excite surface by plane wave, each point of surface becomes a source of some secondary wave, and the secondary wave creates a wavefront. But now if you manage to actually manipulate this interface, change properties of this interface, you can manipulate actually secondary waves generated by the surface and basically redirect the waves in the different directions. This allows you to completely change physical laws because physical laws of refraction and refraction, they do not assume that your surface generate any type of waves. But if your surface actually is a more complicated structure, it's produced kind of effective wave number, which will modulate your phase of reflected on transmitted waves. And in reality, your familiar Snell's law, which enters all books, should be modified by this fact that your surface can present a modulated structure, more sophisticated structure. It's Snell's law is modified by this term, which describe what kind of modulation of surface we have. And that metasurface is actually, it's a very broad, rapidly expanding field. This is from our paper published in Nanoletters. We only shown new directions in this metasurface business. As metasurfaces initially appeared absolutely non-related with resonances, like a possibility to make nanofabrication. So it was new facilities to create structured surfaces in dielectrics and metallic materials. But currently we experience like a new life and with many different applications. So for example, biomedical metasurfaces with different pixels, quantum metasurfaces is very interesting direction. Actually, this is our paper in Science, which describe one of the application of quantum metasurfaces. This is from also different groups. Also hybridization with one layer material with two-dimensional materials allows to create a completely different world of such structures, and with Moira lattices, it's a different fields, and now computational formation metasurfaces. And currently the field is so large that basically people here do not talk to people there. So it's a different type of communities, which, however, unified by general principle of this type of structures. What kind of metasurfaces we may have? If you have an array of different resonators and you manipulate properties of each resonators, this, as I mentioned initially, that's a so-called local a local type of metasurfaces we call local flat optics. And we can also have extended modes here, and we can talk about non-local flat optics. And this different type of application now currently investigated for different purposes. For example, one of the examples which I show here is based on so-called phase change material, vanadium dioxide. This is metasurfaces composed of silicon resonators placed on vanadium dioxide layer placed on the glass. Vanadium dioxide is known as a phase change material. It changed from insulator to metal at a particular temperature if you don't do anything else. But we suggested that we do it all optically, and these are some simulations which shows that different phases, metallic or insulator phase, have different properties in transmission. And our idea was to actually create a structure which will be driven by external light, because it's actually very strongly nonlinear optical structure. And also this very important role is played by magnetoelectric coupling, because as I mentioned, all such structures are driven by two types of resonances, electric and magnetic. And that's what we wanted to achieve, non-reciprocal transmission. This is our structure fabricated of these resonators placed on vanadium dioxide substrate, collaboration with several groups, and the structure is actually realize a highly non-reciprocal functionality. So in one direction transmitted, another direction is completely blocked. So if you draw transmission curves, this has a very clear hysteresis. And this hysteresis, of course, driven by possibility to excite magnetic and electric resonances. Functionalities come from single subwavelength unit self, and it's basically driven by continuous waves at relatively low powers. That's a very recent paper published with Stanford University and with some American colleagues. very recent development associated with the possibility to create resonant metasurfaces, which have a very resonant functionalities. In fact, these resonant metasurfaces are very interesting objects because we associate it with the possibility, if you remember, I mentioned about bound state in a continuum, possibility to actually destroy conditions of completely uncoupled state by introducing small coupling. Small coupling may be introduced by changing symmetry of the meta-atoms elements in metasurface by this simply small asymmetry, which allows you for particular frequencies to propagate and create a very sharp resonant transmission peak depending on properties of these resonators. What is interesting that when the first people tried to fabricate microwaves, then we came with a general theory which allows you to predict why this resonance comes from the generic mechanism of the symmetry breaking, and people started to fabricate this example of fabrication. You see, symmetry breaking is broken in different waves. This is a stop, this is notch, and this is asymmetric bars, slightly asymmetric bars. We all produce sharp resonances. Sharp resonances. How these resonances can be used? I included one example. This is a paper published in Science. 7 years ago, we created a pixelated metasurface. Imagine that this is a 10 by 10 squares. Each square is a metasurface composed of these tilted bars. Tilting produces asymmetry. Asymmetry corresponds to particular peak of reflection of this peak, because all metasurface, each of them is metasurface with specific resonance. So this scaling allows you to introduce a comb of resonances which are relatively overlapping, and this comb of resonances can be used for sensing by the very simple way. So you just project metasurface with specific analytes, and then you see absorption peak. So in reflectance, you see that absorption curve correspond to excitation of some modes of these analytes, and this particular structure can be reflected in this two-dimensional pixelated barcodes. So pixelated barcodes allows you to basically tell you what substances are you using, you're placing on metasurface, because this curve here reflects exactly type of absorption, and absorption corresponds to specific resonances. It's very interesting that the quality factor of these metasurfaces, it's 10 by 10, 100 of metasurfaces. Quality factor is not very high. It's about 140, if I remember well. And it's already sufficient because we need this 100 peak to be overlapped and then follow this absorption curve, and to create these pixels of absorption, which can be associated with specific library to define different type of substances we use for barcoding. That was a highlight in Optics 18. And then we had some follow-up, different type of hyperspectral biosensing based on this method. So this is basically use of sharp resonances in application. Anyway, I come to the end, and I wanted to say that I only presented few snapshots of what's happening in this field. This is a field of resonances. It came originally from the concept of metamaterials, which were based on resonances, but we did not use resonances. Now we use resonances, and we call them metamaterials because they're beyond normal materials with engineering properties. And recently, metamaterials got a new life because using dielectrics, we may move to optics, reducing substantial losses. This new brand names appeared: meta-optics, metaphotonics, depending if you are dealing with individual photons, quantum metaphotonics, depending on if you measure quantum correlations or dealing with individual photons. Of course, resonances are very important. There's a different type of resonances. I just mentioned bound state in the continuum, the Mie resonances of individual resonators, and metasurfaces like two-dimensional arrays of resonances emerge as a new attractive research directions in the originally called flat optics, because but it's not fully flat because we need some thicknesses of order of quarter of wavelength of this material. So it was a lot of applications. There are companies now. Some companies actually push an idea of flat lenses. So basically, if you do photography in a very professional way, you know that you need the huge objectives with several lenses. So now the idea is to replace it by several stacks of flat lenses, and will be much, much thinner with the same functionalities and suppression of aberration. So this is a special activity with the companies which created, but there are many different developments, as I mentioned. Thank you very much for your attention. I believe I did it in time. Thank you.
Exactly in time. Thank you so much, Professor Kivshar. Now we have time for questions and answers. Please raise hands to ask. Sergey Trofimenko, please.
Yes, thank you very much for your talk. I have a small question. At the beginning of your talk, you mentioned about the possibility of interference between electric dipole resonance and magnetic dipole resonance in the sphere. I have a question about it. We know that when we decompose radiation in multipoles, yes, the magnetic dipole radiation is contribution of the next order of magnitude compared to the electric dipole radiation. So I have a question. It seems that magnetic dipole field should be much smaller than electric dipole field. So how can they effectively interfere? Or it is not the case in your problem?
First of all, when you talk about dipole source, it's usually like a point dipole which emits mainly electric field, right? So, but we look at it's much larger object. So this is object which is several hundred nanometers. This object, several hundred nanometer, they can be only approximately presented like dipoles. They are not dipoles. They emit dipole radiation, but they extended objects. In extended objects, a lot of things defined by shape. So because it's a larger object, and then shape, hierarchy of modes also may be changed if you change shape. So you can actually make suppress dipole radiation, electric dipole radiation, enhance magnetic dipole radiation. It's not just as simple as modes of sphere. When you're talking about overlapping, it's not a sphere. It's actually a resonator, cylindrical resonators. If you change shape, you move position of modes. So in sphere, first comes like magnetic, electric, and every mode becomes less and less and less, as you said. But in reality, when you play with shape, you look at cylindrical resonators, you can control modes and position them in intensity. So that's a possibility of shaping radiation. So what you're talking is absolutely correct for sub-wavelength source, which mainly dominated by dipole radiation. But here we are dealing with more extended objects. And then this ratio of magnetic and electric multipoles can be varying. In particular, people are actually engineer modes which electric dipole modes become comparable with the toroidal dipole modes. So it's even higher mode than magnetic dipole, and create so-called anapole states when they suppress radiation of dipole radiation. So it's basically, answer is the shape is not very small. So it's sub-wavelength, but still comparable with wavelength, and shape defines the order of modes, and the higher order modes may become also important. Yeah.
Thank you very much.
So your knowledge comes from the obvious fact that source is very, very small.
Thank you. Understood.
Let's continue. Vladimir Tuz, please.
Hello, hi Yuri. Thank you for your talk, as usual. Excellent. So
You
I
know
have,
everything, Volodya.
yes, indeed. Not everything, because I have one question, actually general question. Actually, the current trend is now to use some artificial intelligence. I see that you have published several papers in this field. Could you say what is your expectation of using this artificial intelligence in the case of metamaterials, metasurfaces, etc.?
No, in terms of optimization, probably that's maybe very important if you use artificial intelligence for optimization. But in general, I don't know. It's a very broad question.
Okay, thank you. So, good.
But Volodya, you knows everything. I'm just really confused. I didn't expect to see you.
Okay.
Можно вопрос? Can I ask a question?
Yes,
Yeah,
sure.
yeah, yeah.
Vladimir Andreevich, please.
I am a bit surprised that you are using these Wigner von Neumann modes. We used to think in spectral theories that they are quite unstable. The generic perturbation, even rather small, will remove them. How do you manage to somehow to keep them not vanishing?
It's a very good question. No, of course, that's why it was no attention to such states whatsoever. But you know, what this modes actually shows. It shows you very specific condition with a quality
Yes.
factor going to infinity. But we don't need infinity. Infinity quality factor useless, because with infinity quality factor we can't couple mode to external radiation. So in reality, in physics, we need several hundred. There are some demonstration of very several tens of thousands, but it's also not very useful. In reality, we need several. I mentioned Q factor 140 for this sensing type of structures, and it's much lower than infinity as you produce by exact state. That's why we call them quasi bound state in a continuum. But the mechanism of suppression of radiation is useful when we try to fabricate such structures. You can't achieve mathematical conditions in physics, but you can, if you know the principle how to suppress more and more radiation, you have a kind of trajectory to improve quality factor. And but in reality, we don't use them. We use what we call quasi bound state in the continuum. If you know, I deliberately did not mention phonoresonances. I put in my article because I remember when I was staying next to the board and Shurik Kovalyov explained some of the results of talks from Kaurovka when he attended. And we put in some peak on the dispersion, not dispersion, but the density of state. And this peak, and Kasevich said, it's a phonoresonance. That's first time in my life when I heard about phonoresonance. So if you think more, quasi-bound state in the continuum are phonoresonances. These are states which appear in the continuum spectrum with the possibility to have a special resonant feedback. And actually, we have a paper which we compared quasi-bound state in the continuum with phono. So basically, think about quasi-bound state in the continuum as a phonoresonance.
So you just need peaks. You just need peaks in density of states, yes?
Yeah, something like that, yeah.
Sharp peak. For example, there are quasi-local modes.
That's exactly the same. But the difference is that phono can be created by two very dissimilar resonances, like a broadband resonance and narrow band resonance. But as soon as I start from bound state in continuum and remove the conditions of the perfect matching, as you said, it's unstable state, it starts to leak. But this leakage is controlled. So basically, I go to the conditions of phonoresonance when I know that the limit of this phonoresonance is bound state in the continuum. So I have a very simple mean to actually control Q factor. So my statement is not every Fano resonance will become big, but every big will become Fano resonance. And that's how we basically control these resonances. Yeah.
Thank you very much. Thanks.
Thank you for question. Yeah.
Andrei Sotnikov, you wanted to ask? Did you?
Yes, possible. Thank you. I would like to ask about the procedure before you fabricate the metasurfaces. Do you use some numerical simulations first to find the proper shapes, or just the
No.
elements?
Of course, we use numerical simulations, and there are many codes which you can use. When we fabricated the first metasurface, that was a very funny story. We had the collaboration with Sandia National Laboratory, and we sent the postdoc, German lady, to Sandia. At that time, we did not know how to actually calculate resonances. And you should understand that if I take resonance, of course, if I start from me theory, these are spheres in air, completely imaginary type of problems. But in reality, you need to have disk and put them on a substrate. It's something completely different. So what this lady, she's German lady, Isabel Stoide, she is now a professor in Jena. She fabricated 54 metasurfaces. She gradually changed parameters, and we wanted to achieve this Huygens condition when the magnetic and electric dipoles responses overlap, and we had no clear theory how to simulate. Of course, now many people can simulate, and Volodya Tus, who is in the audience, of course, he knows that much better than me. We can simulate, but that time we had no idea how to simulate that, and just empirically she came to the conditions when we overlapping them. That was our first prediction of the Skertel scattering, which came from purely theoretical paper. So fabrication is not easy, but of course now we may calculate much more precisely, but still calculation is one story because of roughness and all this fabrication condition, different fabrication places are very different. And for example, the initial structures we fabricated in Oak Ridge National Laboratory. I have a friend who originally from Kiev, who is there and a senior staff member, and he was helping us. But during COVID, they did not maintain the quality of equipment well. They did not service it properly because everything was locked. And after COVID, we did not achieve very impressive results. Our demands are growing. We wanted to achieve much higher Q factors for particular quantum applications, but it was not possible to fabricate there because it's already some pollution, and even in so-called clean rooms were not clean enough to produce a high quality of structure. It was question or?
No, probably not. Next question comes from Oleg Georgievich Turtanov.
Thank you very much for very exciting report, exciting review in the field. I have such a question. How do you think, is it possible in some way to control individually each element of the metasurface to make an analog of phased array they use in radio frequency range for radars to scan a surface and object with a directed radio beam?
Yeah, very good question, because in radio physics, actually, when you talk to radio physicists, they believe everything is done, and you don't invent anything original. And fortunately not. We check, for example, for this strong coupling individual resonators, it was completely missed in radio physics, even if they are dealing with dielectrics. But individual pixel control can be organized in optics, and some people realize that, but of course it's quite technically complicated. But for example, You can control them, but applying voltage on a liquid crystal layer, which sits with metasurfaces. And some realization was reported in Nature Nanotechnology several years ago by a group from A-Star from Singapore. There are some other demonstrations, so the pixel level control is possible. Yeah.
Thank you very much. So it's
technically
possible,
very, very complicated. Yeah.
It's possible to use already developed technological liquid crystals panels, maybe.
Yeah, they use liquid crystals, but we can also use other type of materials. But of course, individually control each unit may be complicated. But if you have a metasurface composed of some pixels, you may try to do that. Yeah, applying, for example, electric field, and yeah, there are different ways to make so-called tunable metasurfaces. Tunable metasurface. Yeah.
Thank you.
Thank you very much. And may I ask one more question? You didn't say something about invisible clocks and so on, this possible use of metamaterials. Is there any application known till now?
It was a lot of hype. I just mentioned how this field came to optics. It came from metamaterials. Invisible clock, apparently research completely disappeared from literature. I believe it taken by military in improving stealth technology, and that's how we don't see much papers on that, you know. But like a fun, of course, people achieve invisibilities at particular frequencies. More broadband invisibility, in principle, can be done, but technically very complicated. But from open literature, we don't see much because it's all taken by for military applications. And you understand improving the stealth technology if you know exactly what to do and how to manipulate with reflective resonances will be very, very important. Yeah.
Thank you. Thank you very much.
Konstantin Alexandrovich, would you like to comment?
Yeah, actually, I have a question. No, first of all, the very excellent lecture, a lot of information, state of the art. Thank you for that. But at the same time, I wanted to ask you if possible to give some information about so-called active metasurfaces, in both senses, active from point of view control, and also a possibility to use metasurfaces for generating or design of oscillators and different frequency bands, if possible.
Yeah, there are many applications. I didn't mention that. There are also different ideas. I can send you some references. There are even review papers how to make them active. I mentioned about tunability in terms of for example, controlling liquid crystal type of response. But also people combine metasurfaces with quantum dots from other type of NV centers. So there are huge. But this raw diagram which I shown, it's just very small fraction related to our interest, but it's so broad topic because idea is just you have resonators and you control properties of resonators, and then you can go in two ways. You can combine them, keeping the properties of individual resonators, or you can combine them to create collective modes. So there are different possibilities of engineering, but very, very current trend is so-called variable technology. So making flexible metasurfaces and using them like a sensors, for example, introducing them into skin and then using this resonator properties for macroscopic type of sensing or reflection, whatever, different type of application, which combine already living organism with this technology, because resonator size is extremely small. If you touch by finger this metasurface, you will not see anything, because the structure this like I said, it's just mimicking nature, but it's a bit different scale, but still you don't feel 100 nanometers size of resonators, but the response will be completely different. Yeah. With active, yes, there are many activities of that. Yeah.
Okay, thank you.
Laser,
You
for
mentioned
example. Yeah.
that you can point for some review on active surfaces.
Yeah, I can send it to you. Just send request and I will send it to you. There are many. I said when I commented that diagram, I probably forgot to mention that people from different directions do not talk to each other now, because it's so deviated. We even don't know what's happening, because people, for example, this quantum people, we don't talk to people who are doing two-dimensional materials if it not involve quantum type of properties, or people doing biosensing basically come from biology or chemistry. It's so diverse. Only this year, it was a free papers which with the name roadmap in. Now it's fashionable to pub roadmaps. So many authors are combined and write something specific about the field, and then huge article appear, which is called Roadmap in Metasurfaces. So there we have 3 huge articles with the name of Roadmap published in Applied Physics Letters, Journal of Physics, and ICS Photonics. And can you imagine, overlapping of authors is very, very small. I'm probably the only one who appears everywhere, but still it's a very different directions, and people do not overlap much. It's a huge activity now. Yeah.
Okay, thank you very much. Thank you.
If you send me email, I will send you some references if you're interested.
think
Not even references, but papers, you may not get access.
Okay, thank you very much. I will try Andrei Sotnikov to help me with this.
Okay.
Okay. Yuri, you mentioned people from different backgrounds, and also Vladimir Tuz asked you a general question. Another general question: what's your opinion about quantum metamaterials? What if the meta atoms have something to do with quantumness? If they can be in a positional state?
That's a good question. It's hard to say. I have 2 review papers with the name of quantum metasurfaces, and I actually try to go deeper into that field. Of course, there is a term which called quantum metasurfaces. This is metasurfaces which created by quantum particles, for example, like atoms which are trapped in an atomic lattice with the specific properties of emission. So they just really controlled by quantum elements. It was a few demonstrations, but again, in terms of application functionalities, was quite limited. But there are also what people call quantum metasurfaces, just metasurfaces for quantum operation. This is completely different. So metasurface may be used like a multiple source of SPDC. That's many sources which interfere. You can do different operation with the help of metasurfaces. That's a different story. So metasurface is not quantum, but it helps to operate with the single photons and with bunches of single photons. This is a type of that functionality. So problem here is that it's not yet clear what will be winning strategy, because always when you have some new technology, people ask what is the advantage of this technology, why we can't do it by normal means, and that's obviously should be answered. But it's only beginning. People try to demonstrate some interesting functionality with multiple SPDC operation and imaging. For example, if you're talking about quantum imaging, clear that you need something extended, and source of quantum photons should be placed on some surface, and that may create some interesting functionality for applications. There are few review papers. I can send it to you if you are interested, but I found it a bit difficult because you need more experienced people in quantum field, and my background is not quantum, even I try to apply it for quantum application. I always collaborated with someone who is much smarter than me.
Thanks. I'll check the review papers. Next question from Konstantin Sirenko, please.
Hello, thank you for opportunity and such an interesting talk. I have a question regarding the Me voids and the Nano-Kandinsky object. So the colors exhibited by these voids are unlike the diffraction gratings where different wavelengths go to different directions. And in this case, it could be seen from any viewing angle, right?
Yeah, because it's individual resonators. Yeah, they don't talk to each other.
And you enlight them with a white light to see the colors, or how it's...
Yeah.
Okay, thank you.
So this it's an interesting feature because voids created by light trapped, the voids is empty spaces and light trapped in open areas in air. And because of these walls who trap light, there is very small leakage outside. These evanescent waves are very weak. So there is no strong overlapping between modes of different voids. So it's an individual effect. Of course, such structures can have diffraction, but this operation is outside of diffraction condition. Yeah.
So each resonator, each void is like a pixel of a picture, basically.
Yes.
Thank you.
Zoe Yeremenko, please.
Yuri,
Alexander Semyonovich, would you please wait a minute?
Thank you so much for your wonderful talk. And I have a question. Can you say something about refractive near-zero refractive index material? If yes, how can we observe experimentally this resonances in such regime?
This is active field. Yeah, people try, but not maybe. It's interest a bit decaying in some sense. It's people, when people started to study this zero index materials, it was a lot of fun, something, as you understand, something unusual. But in terms of application, I do not see many applications. So one of the application which actually was impressive is that if you look at the nonlinear properties and you go to point of zero index is actually a dominator of nonlinear path. So basically, you by going to the regime when index becomes zero, you enhance nonlinear response, and that was a kind of interesting property which people use. From the other side, if you can if you pass index through zero, then you can use basically elements which will operate like reflectors and transmitters, and that also people use zero index layer to separate, for example, fundamental and harmonic field, to localize in fundamental and transmitting harmonic or reverse. So I don't see it's a very funny concept, very useful, and people are using them for different application, but I would not say it's too broad and systematically presented in different applications. Some applications people use that, but one which I remember and actually was involved in the possibility to enhance nonlinear response through going to zero. Again, you can't do exactly zero, but approaching vanishing index through these conditions. Yeah. Actually, currently, I mean, I'm not sure you know about that. If you follow properties of materials and take silicon, silicon actually becomes metal in UV, and that's people try to use because they can create a transition between full reflection through this negative index, negative epsilon, and transmission. But again, it's not a metallic properties, it's like a polyretonic properties in UV from silicon. Yeah.
Thank you.
Thank you.
Alexander Semyonovich, sorry that I interrupted you. Please ask your questions.
Shurik.
Yuri, what's about the artificial arrays and two-dimensional artificial letters of magnetic nanodots? Because the question of internal modes in these nanodots are widely studied now. And isn't this area of magnetism something similar to the ideas you said about in optics, for example, in magnetic?
I don't know. I did not see that. I did not see that, and that's actually maybe I just don't know. Yeah, nanodots are used to make metamaterials active, but I don't know if they differentiate between electric and magnetic. I did not see that. I need to search it and check it. Yeah, some groups are trying to push it for imaging, for quantum imaging, but I just don't know.
Thank you.
Probably enough for today. I do not see other questions. Also, Professor Kivshar is probably available via email if you have more questions.
I am happy to answer any questions, and for email, just type my name and you will find I have 3 emails from different sources, and everything working combined on my computer together.
Thanks a lot. You responded to so many questions for more than 30 minutes in a row. I have an idea, dear participants. What if you make a group photo? May I ask everybody to switch on cameras, and we'll try to make it. While you do so, there were more than 100 participants of today's seminar, and of course it will be watched if we manage to download the video. Please switch on your cameras, and Andrei, will you make a photo? Is it possible?
Yes, I am sorry. So we have plenty. So still participants are turning on the cameras. So
I can try to switch because I have now 7:30 p.m. So no.
Perfect.
Wonderful. Thank you.
Oh, a bit better, right?
Yes. Let's wait a few more seconds. Meanwhile, I'll invite everybody to our next seminars. And also today is Professor Kharkiv is here. Today they have another quantum seminar at 2 o'clock in Cal. We invite everybody to our next seminars. Andrei, tell us what to do.
Yeah, I took the pictures, so thank you. Thanks all for participation.
So,
so 3, 2, 1.
Repeat, maybe.
Goes. Yeah, wonderful.
Can you put my name in your subscription list to have information?
Certainly, yes.
If you don't mind.
Most of our seminars are too late for you.
At least I will know. Yeah, I will know. Maybe something very interesting. Yeah.
Professor Kivshar, thank you so much for.
Thank you for inviting me. Thank you.
An outstanding lecture, and coping with all our questions. Thanks to everybody for participating.
Happy to answer emails if you have. Yeah, sure. Thank you. Thanks so
Thank
much.
you.
All the best. Bye-bye.
Bye.